Okay, thank you for the invitation and thank you for the introduction. So today I'm going to talk about what I call the periodic symplectic cohomology and the corresponding Hodge filtration that you can define on them. So to define this thing, let me first recall for you the formalism of homological mirror symmetry for open manifolds. So the kind of mirror symmetry I'm going to think about that on the A model side, we have a symplectic manifold, which is open. I could add the condition on this either exact or monotone so that you know there's good Floer theory on them. And on the B side, such an open manifold usually is mirrored to a Landau-Ginzburg model. So let me call it M check. So this is usually a complex algebraic variety. And the Landau-Ginzburg model is given by a regular function or a holomorphic function, 2C. So if you want to have a tiny example in mind, you can take M to be P1 minus the pair of points. And M check will be the matrix factor, it's the superpotential on C star to the third. That's given by X, Y, Z. Sorry. Yeah. Okay, so in this setting, the open string invariant we usually look at is, still, I think Amy talked about this last talk, is the rough category associated to M. And on the B side, you have the matrix factorization of W. And we want to take, we want to look at the closed string analog of these. So by this we mean I'm going to take something called the Hodge homology of the rough category. On this side, it's a conjecture first by Seidel and proven by Ganatra. Under the assumption that M has the rough category has enough object, this is just the symplectic homology shifted by a certain degree. And if I look at the matrix factorization side, so I will take the Hodge homology of matrix factorization. Since I don't assume M is affine or any assumption on it, this is isomorphic in general to the hypercohomology of M check with values in a twisted Dirham cohomology complex. Sorry, I don't have enough space. Maybe. Okay. So roughly what you should think of is that if my superpotential is 0 and my manifold is actually affine, this is some analog of the Hodge-Rosenberg theorem. That's Hodge cohomology is just differential forms on one side, right? So in this setting, this is a theorem of Efimov. we'll assume M check is a quasi-projective variety. And the critical locus of W is inside, is supported on the inverse image of 0. Okay, so on the other hand, on this side, Fimov also proved that you can take something called the periodic cyclic homology of the category. This is still isomorphic to the hypercohomology of M, but now instead of this twisted dynamical chain complex, you'll be looking at the oh, sorry. I should really start another line. So therefore, double complex with two differential. One is given by the original twisting differential, dW. The other one is U times the DRAM differential. So again, if you don't have a superpotential, this is the DRAM cohomology of this is the holomorphic DRAM complex of M, and then what this thing is just after taking this differential becomes the usual DRAM cohomology of the underlying manifold. So so that's the general story here. Maybe any questions so far? I know it's a bunch of symbol, maybe. So, okay. So, since if there's no superpotential, what you really get is just a DRAM cohomology. You might expect there's some Hodge theoretic invariant you can put on this. So in fact, if say the category, a differential graded category is what's called a smooth and proper, then there's a work of Kazakov, Mitsevich, Attentive, who puts a non-commutative Hodge structure on this periodic cyclic homology of A. And sort of you want to know what's well, now I cannot really reach the top, but you want to know what's the analog on the symplectic side. Yes? Define, or what do you want? Oh, I mean, yeah, I mean, since I'm in smooth and proper category, then I know there's a degeneration. I guess once you choose that splitting, you have this. Yeah. I mean, Yeah, I mean, I wasn't being precise. So their notion of non-conveyor Hodge structure have twofold. One, the first fold is some derived data, which is just well, it's a little. So it's a meromorphic connection that you can define on a formal puncture disk, which maybe have a irregular singularity at 0 that, or regular singularity which can be extended to a holomorphic bundle with a flexion connection, either a flat connection or with some stock data. So I mean, there's a bunch of things you have to list. But
is there an anti-Hodge?
no, this is the RAM data. Then there's a Betty data. Then that contains some first of all a rational structure, and then an integral structure which relate to this gamma integral structure. I think. I mean, so far I wasn't being any precise because I didn't want to give the full definition. Maybe that's confusing. Okay. Anyway, so, but the problem that I want to address in this case is that so if I'm in a full setting of homological mirror symmetry for open manifold, the categories that you're looking at, for example, the rough category, is shown to be smooth, but it's not necessarily proper, which means that if I look at the cohomology of the Hom inside this category, say the rough category between two objects, this is not finite dimension. Sorry. And the corresponding phenomenon on the B side is that, for example, your superpotential W does not have a proper critical locus. So I think all the work so far on this side has been done is all for either proper locus, even in their paper, or isolated singularity.
When you stated the theorem, it didn't say anything.
You mean for Affiliation theorem?
Yes.
Yeah, but I'm a little confused about his theorem at the moment because he didn't say anything. So this is the correct assumption. But somehow, yeah. Yeah, maybe he has something worked out. But, okay, but there's some phenomena you're gonna see later, like how exactly this condition gonna matter in this story. Okay, so the goal of this talk is just to tell you you may possibly, so I'm gonna propose a new version or new definition of this periodically homology on category for A equal to the rough category of M, which might have good properties. I mean, there are some, yeah, I'm gonna explain it more, sorry. This is just motivation. Okay. I'll use here. So, to do this, first I want to define for you what are these notions. So here is just all, I haven't tell you any definition yet. So let me first tell you something. So cyclic homology of mixed complex. So for me, I want to think of a mixed complex that I'm going to define for you. Consists of the data C, D, and delta, where the C is a sigma 2 graded K module over some ground field, and D and delta are all degree differential. So that such as the anti-commute. Okay. So let me give some example of these. So example A is sort of the prototypical example on the A side. So let's begin with a finite dimensional manifold. And let's assume there's an S1 action on X. Okay. So I want to consider, say, the singular chains on X. Since I have an S1 action, I can define a differential graded module structure over the chains on S1, where this thing has a differential graded algebra structure under multiplication on S1. And this module structure is just like given by cross product, and then you just act by the action. Okay. So in this case, well, there are some slight things I need to do. I want to think of sort of this chains on S1 is isomorphic as DJA. 2 is homology. So this is really a ring that's generated by, say, epsilon with epsilon square mod out. That epsilon has a degree 1 in this situation. Okay. So this means that I can, sorry, I really need more space. So you can try to work out what does this mean under what's this differential graded module structure. So I have 2 elements. One is identity X trivially on the chain complex. Then I can multiply by epsilon, right? So I get an operation, say, which is multiplication by epsilon on the chain singular chains. So, and I know there's a relation that delta square equal to 0. And when you work out the differential graded module condition, there's a Leibniz condition that turn into this condition here. Well, so I'm being a little bit, I'm lying a little bit that to really write down this map, I need to pass to a normalized singular chains, and so I'm trying to like transfer the structure. Well, that's just something aside. But in this situation, you really, so this is the condition we want. You really just get a mixed complex, where this is basically multiplied by the S1 action. Sorry, I really need to. Example B is, well, so maybe let me be brief. So on the B model side, you sort of just have a superpotential on the mirror side. And let's assume M is alpha, and W has an isolated singularity. Well, I think I don't really need this, but just assume this. Then you can look at the holomorphic de Rham complex. It's the same complex we're looking at over there. And you can check that if I define a differential here, 1 to be wedged by dw, and the second one being the usual exterior derivative on that, you can check this satisfies the condition, which is exactly the model you're using here. Okay. So that's the example I'll give it to you. And so given such a mixed complex, so definition is that, yeah.
Don't these two differentials go in the same direction?
Yeah, but it's a all degree differential, so it's okay. I mean, if I have if this is a Calabi-Yau, I can try to write down. I mean, in general, this, you know, this chain complex I will write is a Z-mod 2 graded. Everything is Z-mod 2 graded in this case. I don't assume I have a Z grading at the moment. So given, okay. So given this data, what you can do is cook up 3 chain complexes. The first one I will call C minus is here is what this means is I'm taking formal power series in U with coefficient in this chain complex. And I can consider its localization with respect to U. Then this is nothing but the formal Laurent series. With coefficient in C. And let's say C plus is C hat. Sorry. Is a quotient of this chain complex by multiplication of the other one. Okay, so these are 3 chain complexes that you can look at. And later it's gonna be important. I'm gonna point out I'm taking formal power series in this case. So I'm taking certain U-adic completion, we'll see. And what these complexes are is that once. Oh, yeah, I see. I think I'm running out of time.
I have 100 what you divide by, is it U times C?
U times the formal power series part. So after you do this, this thing sort of isomorphic to everything in the negative degree, but not as you know, CU module or something, KU module, sorry. So the data of a mixed complex you can check. The only condition I have is guarantee that if I define a big differential, and I call D plus U, oh, sorry. Here I didn't say, U is just a formal variable of degree 2. In the Z-mod 2-graded case, you just take that to be 0. I mean, if you have a Z grading. Okay, so then you can check D squared equal to 0 by the assumption. Okay, then let's define your differential on each of these chain complexes. And then the theory of cyclic homology will say if I take homology of this, the first one is called the negative cyclic homology. The second one is the periodic cyclic homology I was talking about, where you can start to take that example. The last one is just the usual cyclic homology. Okay. So roughly these things, why they matters is that, sorry, I think I will just comment on this since I want to go into my construction, is that, now I have covered my board. So why you want to consider is that the DRAM part of the data for a non-commutative Hodge structure is that the homology of this, if it's a smooth and purple category, that will give you some free module that over K U K formal Laurent series. So that's, you can think of as a vector bundle over the puncture disk. And then what you need to do later is that define a connection that may have meromorphic singularity at 0. And then the negative cyclic homology is also it might have torsion in general, but if the Hodge to DRAM degenerate, then this thing can be shown to be a free Z power series, C power series module. So that you can think of as a vector bundle. Sorry, Paul, you seems confused, maybe. I'm not really saying precise things, sorry. Okay, so then I just want to, so this is the formal structure that you have. I want to apply these things on the symplectic side. And to do that, I want to tell you sort of a mixed complex structure that you can define on the symplectic quotient complex. Okay, so let me me define what I mean by this periodic symplectic homology. Okay, so the setting again is an open symplectic manifold. I want to restrict to myself to the case that I have an exact symplectic manifold just for the sake of presentation. So consider an exact symplectic manifold which is conical and convex at infinity. This means that this thing is of the form that's a compact piece. And on the at infinity, you just have a sort of a symplecticization. So the picture is like this. I have some interior part of this compact manifold, and I have a so the boundary of this is assumed to be a contact hypersurface. So what this means is that if I restrict this one form that I have, so first of all, this one form will define me some symplectic form in the interior. And if I restrict this one form to the boundary, I get some contact form. And on the conical part, the symplectic form really looks like a symplecticization. So where R is the coordinates here. Okay, so example of this, such a thing, the easy example you can take is just M is a cotangent bundle of a closed Riemannian manifold. And theta is just a canonical one form. And this interior part is the usual disk bundle. Okay, so really the disk bundle is the interior part on the, at the infinity you just have a cone modeled on the sphere bundle. Given by the metric. Sorry. So I guess most people are familiar with this. So this is the setting where you can define Floer theory and or symplectic cohomology on the exact manifold. So very briefly is that okay, so given some time-dependent Hamiltonian, I will specify what do I want later. So this is just some function on M to R. What you can look at is the associated action function on the loop space of M. So in the setting of Hamiltonian Floer homology, this function can be assumed to be Morse, or it's an infinite Morse function. A Morse function on the infinite dimensional space. And roughly the symplectic cochain complex I'm going to define. So this is a cochain complex. It's generated by all its critical points. Really, in this case, you can check this is identified to Hamiltonian orbits of xh. Sorry. Okay, and then you should differential just count flow trajectory of this kind. So if you think the picture, so this thing doesn't really have a gradient defined on the loop space, but it has a well-defined partial differential equation you can define on M. So you will count this flow trajectory of this kind. So on both sides is a generator, is some loop generated by the Hamiltonian. I'll just assume this solves the flow equation for. So this carries some gradient equation. Okay. So solves the flow equation for this function. And the important thing I want to say is that you can define the BV operator. So I want to define the other operation for you. But it's sort of obvious that on the loop space you will have a circle rotation. So let's see. So you can define S1 action on the free loop space by just rotating the loops. Okay, I want to capture this action by an operator called delta. In this case, it's the BV operator. That just counts solutions in the moduli space like this. So I will have a pairs. One is the angle in S1. One is a flow trajectory that, so for each of the flow trajectory, their natural parameter has an initial point. So instead of putting, you can put the Hamiltonian on this side by ht, and the other side you can exactly rotate this. So that's you're changing your starting point by theta, right? And then you can define an interpolation between these two Hamiltonian to be a one-parameter family, and then this U just solves the gradient trajectory equation for this family. Okay, and you can check this gives you operation. So before I could there's an R action on the differential that I can model it out. But here, since I'm taking a one-parameter family depending on S, it doesn't have a S1 action anymore. R action anymore, and this family is naturally parameterized over S1 by projecting to the theta coordinate. So this operator, you can check, define for you some operation on this for each ht, degree -1. Before, let's say the differential that I set up for the degree is just +1 for convention. So this 2 differ exactly by 2. Okay, and then using this, well, I can define a S1 differential like before, but the only difference is, in this case, my delta square might not square to 0, but I'm going to ignore that. So let's just take this. In general, I might have a higher order term in U. So this is sort of written down in a paper by Seidel and Bourgeois and Elcher, if you want to really read about it. But in this case, I can take this S1 differential and consider this symplectic quotient complex. So I already have something like a mixed complex. I just need to take its periodic cyclic homology now. There are two cases you can consider. Case one is sort of like I can take a Hamiltonian. Let's go quadratically, and I would consider a small time-dependent perturbation of this. So the naive definition for the periodic symplectic homology is that you're just gonna take your entire symplectic quotient complex that consists of Hamiltonian of all the possible Hamiltonian orbits that you can get for the quadratic differential. And I'm gonna consider, to take the periodic version, I'm gonna consider the Laurent series in this. And then the natural ds1 will give me, that I defined here, will be a differential here. Okay, so the problem with this chain complex is that this thing is usually infinite generated. And since we're taking this U-adic filtration, which is complete in the positive direction, then you might run into some certain completion problem that, for example, now if I take homology, so this is what you should take as your periodic symplectic homology, which I will call HP of M. So this thing is sort of completed respect to multiplication on U on the chain level. And the problem here is that, for example, in the case my M is really just a cotangent bundle. It's known that this symplectic quotient complex, whatever you do, is sort of just equivalent to homology on the free loop space. And then you know that if you take a periodic version of the S1 equivariant homology of the free loop space, there's a theorem by Goodwillie which says that this, whatever you get, only depends on the fundamental group of the base. So the problem is that, for example, if Q is simply connected, then I really just get a trivial. This thing is just rank 1. You don't get anything interesting. So that's why I'm saying at the beginning, you should not just take the naive periodic cyclic homology of the category. Okay. So this thing, I'll call this sort of like a completed. It is symplectic homology. But there's another thing you can do is that sorry. I could, instead of taking a quadratic Hamiltonian like this, I will just take a linear Hamiltonian of certain slope k. So on the example, for example, M is just T star S1. The corresponding Hamiltonian orbits you get is that you get some critical point on the interior, but for slope, say you can arrange things so that for slope 1, you just have 2 closed Hamiltonian orbits, and then for slope 2, you just have 2 of them. So this is the generator for F star 1, and this is generators for coaching complex of slope 2. So really here, in the case of cotangent bundle, each of them is by projection corresponding to a closed geodesic on the base. Then what we want to do in the second case is that I will just take the Floer coaching complex for this for the linear Hamiltonian, and consider the corresponding periodic theory in this with the same equivariant differential that I defined. And I first will pass to homology with respect to this, and but somehow my chain complex still depend on the Hamiltonian that I take. Then in the end, we're just gonna take direct limit over k. So say, let's call this the second homology theory that we can define. So in the case of, for example, T star S1, what you're really doing is just you're first filtering by length of the geodesic, and then consider the localized S1 equivariant theory. And then you take a direct limit over all this, so it's sort of a finite dimensional approximation for your loop space. And in this sense, that this chain complex, you can really also think of its first take a homotopic direct limit of all those finite dimensional pieces, and then so that it is and so then you get the homotopy type of the entire loop space, and then try to do localization. Okay, so in this case, the theory that I defined for you, I put a loc here. Sorry, I'm really running out of time. So the upshot of all this is that one theorem from 2014 is that if you're given me an exact symplectic manifold, and if I consider this localized version of periodic cyclic homology for M, this is really isomorphic to the cohomology of M that you started with. tensor in the round series ring over Q coefficient. Okay, so since I don't have enough time, the proof of this is not particularly hard. You just have to think of, for example, I have a S1 action on the loop space. What are the stabilizers that I get for each generator? Then it's really just for each multiplicity or length k geodesic, you get a stabilizer is lemma k. Such a thing is classifying space over Q doesn't contribute to the localized when you do S1 equivalent localization. Well, maybe I can elaborate more. Okay, so what I want to remark is that so this is the case for exact symplectic manifold. If your M is not that necessarily exact, for example, monotone, so the corresponding localized series of M. So this is a setting that your interior is monotone, but on the boundary, it might be exact, the one form. Okay, so this thing, if you do a similar argument like this, should be isomorphic to quantum cohomology of M with Navikov coefficient, certain Navikov coefficient, with still the same power series. Here I need to really take characteristic of k equal to 0, so that I have a localization over Q. So all I'm saying is the same sort of arguments still work if you don't want to work in the exact case. And sort of this isomorphism is given by the usual PSS map that you can take a chain on the quantum cohomology and send it to a Hamiltonian Floer. Well, then the difference is here with the usual quantum cohomology is that this one doesn't, the M isn't compact in this case. Okay. So maybe I have a little bit of time. You might think that this thing is particularly non-interesting because everything we get just localized to homology of M. But what I want to propose is that you can still put think about the categorical Hodge filtration on these things. On the corresponding periodic cyclic homology that I defined for you. So the thing is like you could consider this version. And sometimes if your rough category is, say, proper, the two theory agree. But this version, if you just use this version, somehow there's no meaningful things you can put on the periodic theory, because if a manifold is a, say, cotangent bundle or of a simply connected manifold, this is really just isomorphic to a ground ring. So it doesn't carry any interesting structure. On the other hand, you can try to think of what's the corresponding filtration you can put. So, sorry, before I do that, let's just really define this thing for you. So, in this case, I can really just take a closed open cyclic closed open maps to instead of taking the periodic cyclic homology of the category, I could just take the periodic cyclic homology of the closed sector. Then the corresponding filtration you define is that for each HK, so I'll just define for you, say on this even part, since I'm Zima 2 graded, okay. So this filtration, what is that? Sorry. Oh yeah, okay. It's all the classes, so that on chain level, so I have this is really a filtration on chain level that's induced on the homology. Sorry, maybe let me do this way. So let's first define it on the chain level. Okay. What this is a filter P piece. Okay. It's everything that can be that's we are filter respect to Euryaltic filtration. So I can write this in terms of power series. So really here, AI is a generator of the symplectic Hodge complex, HK. Okay, and this is everything that's a power is bigger than P, that's naturally a filtration. I mean, it's the same filtration that you want to put on periodic cyclic homology theory. Okay, but the problem, then the thing is, I'm just taking one particular HK. You will want to take a direct limit. After taking this, you want to take a direct limit respect to HK. So somehow this will descend to filtration on this localized version that I was talking about. Just by taking the corresponding homology filtration and then take a direct limit over all such a HK. Okay, so, and again, this thing, either which version you are looking at, it's rationally the cohomology of M, or the quantum cohomology of M. Well, and I sort of want to convince you this filtration, if I have time, is not a naive filtration. So this filtration is like asking if you have a homology class, when can it be presented on the chain level as some classes coming from the filter piece, right? So. Let me think how to do this. So maybe let me just mention one thing, is that, in the case, so if you look at this theorem, what does it say? is like if I have elements in equivalent symplectic homology, since the localization holds, if I do localization in this way, it's saying like after localization, any equivalent classes living symplectic homology can be written as classes in the interior with some polyzer, Laurent series of sum. So sort of you can ask, if I give you some S1 equivalent class, what kind of cohomology class you will get on the other side. Okay, similarly true on this here. So maybe I'll just briefly mention that. So in the setting of if M is really a complement of a divisor, that D is assuming to be, say, M is monotones, and D is, say, one of X. Sorry. Yeah. In this situation, I think there's some work by Paul Settle that's have some implication that if you look at a certain S1 equivalent cohomology class, that you can put on the complement of anti-canonical divisor, then you can look at the corresponding classes coming from cohomology, and of course this filtration sort of filtration on the localized version encodes a certain say Gromov-Witten invariant. So the correct answer is that well, the classes that are coming from cohomology, maybe you can think they're defined by some classes given by Gromov-Witten invariant, maybe possibly equipped with gravitational descendants coming from the divisor. Okay. I mean, I didn't have time to say this precisely. I'm sorry. But this is one usefulness that I want to propose, that this filtration may give it to you. Okay. Inserted. Sorry. Maybe I will just stop here. I'm sorry. Yeah. If you have a